The ground beneath your boots on Mars is splitting open. A jagged crack tears across the rust-colored dust, and for a terrifying instant it looks like the entire crater floor might swallow you whole. But this isn't happening because of anything stirring deep inside the planet. It's happening because something slammed into Mars from space, and the shockwave just reached you. For years, scientists assumed Marsquakes came almost entirely from the planet's own restless geology, ancient rock cracking under heat and pressure far below the surface. Now, a shocking new discovery built on artificial intelligence and years of NASA data has turned that assumption upside down. Researchers have found hard evidence that a startling number of these quakes are actually being triggered by meteorites slamming into the Martian surface. And the planet is getting hit far more often than anyone predicted, roughly 2.5 times more frequently than earlier estimates suggested. New craters are forming right now, more often than scientists ever imagined. And the shockwaves from these impacts aren't just rattling the surface. They're punching straight through the crust and racing along a previously unknown seismic highway deep inside the planet, exposing an interior that behaves nothing like the model scientists have relied on for years. The single discovery has forced NASA to reconsider what it thought it understood about the inside of Mars. And the obvious, unsettling question left hanging in the red dust is simple. If the planet has been hiding a structural secret like this the entire time, what else is still buried beneath the surface, waiting to be found? To understand how researchers got here, you have to go back to a mission that already seemed finished. NASA's InSight lander touched down on Mars on November 26, 2018, after a launch that almost didn't happen on schedule. It was originally supposed to lift off in March 2016, but a vacuum leak in its seismometer forced NASA to delay the entire mission until May 2018. That delay wasn't cheap either, pushing the total cost of the mission from an already substantial $675 million up to roughly $830 million. Once it finally landed, InSight's entire purpose was to listen. It carried a highly sensitive seismometer called SEIS, short for Seismic Experiment for Interior Structure, a French-built instrument so precise it could detect ground movement smaller than the width of a hydrogen atom. That level of sensitivity mattered enormously, because unlike Earth, Mars doesn't have obvious surface clues like mountain ranges actively colliding or volcanoes erupting to tell scientists where the geological action is happening. Almost everything researchers know about the deep interior of Mars had to be reconstructed indirectly, purely from the whisper of vibrations traveling through rock. Over the following 4 years, InSight recorded more than 1,300 separate Marsquakes, a treasure trove of seismic data that scientists are still combing through today. Some of those tremors were assumed to come from underground rock fracturing under heat and pressure, the kind of slow internal geological stress you'd expect from a planet that once had a molten, active interior. Others were suspected, but never confirmed, to be the result of meteoroids crashing into the surface from space. InSight itself didn't survive forever. Dust slowly built up on its solar panels because the landing site simply didn't get the strong wind gusts needed to blow the panels clean. By February 2021, during the Martian winter, dust had reduced the lander's power output to just 27% of its original capacity, forcing NASA to put it into a hibernation mode that shut down instrument after instrument to conserve energy. In May 2021, engineers found a clever workaround, using the lander's robotic arm to pour sand near the panel so the wind could carry some of the dust away, briefly restoring a bit of power. But the decline continued. By July 2022, NASA had shifted InSight into a low power mode just to keep the seismometer running for as long as possible. The lander finally lost contact with Earth on December 15, 2022, and NASA officially declared the mission over on December 21, 2022. But even after InSight went silent, its data didn't stop being useful. In fact, it's now at the center of one of the most unsettling discoveries about Mars in years. Here's where the story takes its strange turn. Researchers took that massive archive of Marsquake recordings and compared it against fresh impact craters spotted by NASA's Mars Reconnaissance Orbiter, a spacecraft that has been photographing the Martian surface for years. Normally, matching a specific seismic signal to a specific crater is an incredibly slow process, the kind of painstaking image-by-image comparison that could take a research team years to complete by hand. But this time, scientists brought in artificial intelligence to do the heavy lifting. Instead of manually sorting through tens of thousands of orbital images looking for signs of a new crater, machine learning tools scanned the data and narrowed the search down to a manageable set of candidates in a matter of days. The algorithm was trained to spot the telltale dark blast marks and radial streaks that fresh impacts leave scattered across the reddish Martian dust, signatures that fade over time as wind slowly reworks the surface, which meant the AI essentially had to be taught to recognize impacts that were geologically young in a place where almost everything else looks ancient. Researchers focused specifically on the region within roughly 1,800 miles of InSight's landing site, since that was the area where the lander's seismometer would realistically be sensitive enough to pick up an impact-triggered tremor. Comparing before and after images from the orbiter's context camera, they identified 123 fresh craters that had formed sometime while InSight's seismometer was actively listening. From there, the team cross-referenced each of those newly formed craters against the catalog of recorded Marsquakes, searching for matches in timing and signal strength. That process narrowed the list down to 49 craters that looked like plausible matches for specific seismic events already sitting in InSight's data. After further analysis, one impact site stood out above all the rest. A crater just 71 feet wide, located in a region called Cerberus Fossae. And this is where things got genuinely unnerving for the scientists involved. Cerberus Fossae sits roughly 1,000 miles away from where InSight touched down, a considerable distance for a seismic signal from a comparatively small impact to travel and still register clearly. Under the old assumptions about Mars, the planet's thick crust was expected to absorb most of the energy from an impact like this, dramatically limiting how far the resulting seismic waves could actually spread. A crater that size, that far away, shouldn't have produced a signal strong enough to reach InSight's instruments at all, at least not according to the models scientists had been using for years. But it did. When researchers dug into exactly how those waves traveled, they discovered that instead of getting dampened and scattered near the surface the way the models predicted, the seismic energy from the impact took a much more direct and considerably deeper path, cutting straight through the Martian mantle like it was following a hidden channel. That's the discovery researchers have started calling a seismic highway, an unexpected pathway running through the interior of Mars that allows the shock waves from meteorite impacts to travel far greater distances than anyone believed was possible. It's not a comforting thought. If seismic energy can shoot straight through the planet's interior instead of being absorbed near the surface, it means the internal structure of Mars is fundamentally different from what NASA's models have assumed for years, which means scientists now have to go back and rebuild those models from scratch. It also means that this quiet, seemingly frozen red world has an unstable interior capable of transmitting massive amounts of energy in ways nobody predicted, and researchers are only now beginning to understand what that could mean for the planet as a whole. One theory gaining traction is that this hidden channel might trace back to old volcanic plumbing, ancient conduits once used by molten rock rising from deep within the planet, now cooled and solidified, but still structurally different enough from the surrounding mantle to let seismic waves travel through them with far less resistance. If that's true, it would mean Mars's long-dead volcanic past is still quietly shaping how energy moves through the planet today, centuries after the eruptions themselves stopped. There's a second layer to this discovery that makes it even more important, and it has to do with how scientists interpret the seismic data they've already collected. Cerberus Fossae wasn't just a random spot on the map. It's one of the most seismically active regions on all of Mars, a place researchers had already flagged as producing a huge number of high-frequency Marsquakes. For years, the working assumption was that most of that activity came from processes happening inside the planet itself. Ancient volcanic fractures slowly settling, rock grinding against rock deep underground. But this new evidence suggests that at least some of those signals researchers had been attributing to internal geological activity may have actually come from meteorite impacts landing in or near that same region. In other words, scientists may have been quietly misreading a chunk of their own data for years, mixing up quakes caused by space rocks with quakes caused by Mars's own restless interior. That distinction matters enormously because if researchers can't reliably tell the difference between an internally generated Marsquake and an impact-triggered one, every conclusion built on that data becomes shakier than anyone realized. This discovery gives scientists a genuine, confirmed reference point, a known impact matched to a known seismic signal, that they can now use to go back through years of InSight's archive and start sorting real internal tremors from disguised meteorite strikes. It's essentially handing researchers a decoder ring for a mountain of data they thought they already understood. And the ripple effects go further than just Cerberus Fossae. Every region on Mars that InSight ever picked up seismic activity from now has to be quietly re-examined with this same suspicion in mind, because if impacts were being miscounted as internal quakes in one of the most studied regions on the planet, there's a real possibility the same mistake happened in areas researchers assumed were purely tectonic. And here's the part that should genuinely make you pause. If Mars is getting struck by meteorites roughly 2.5 times more often than earlier estimates suggested, that's not a small correction. It's a complete shift in how dangerous the Martian surface actually is on any given day. Earth is largely protected from small meteoroids by its thick atmosphere, which burns up the vast majority of debris before it ever reaches the ground. Mars has a much thinner atmosphere, only about 1% as dense as Earth's, which means far more of these space rocks survive their descent and actually reach the surface intact. Combine that thinner atmospheric shield with a genuinely higher impact rate than previously calculated, and you get a picture of a planet that is being pelted with far more frequency than scientists ever accounted for in their models, a place where new craters are quietly appearing all the time, often without anyone noticing until an orbiter happens to photograph the same patch of ground twice. Some researchers now estimate that dozens of new craters large enough to be spotted from orbit form across the Martian surface every single year, a pace that, once you account for the smaller impacts too faint or too small to easily detect, could mean the planet is being struck on a near constant basis. For any future human mission to Mars, that's a detail worth taking seriously. A planet that's being struck more often than expected, with impacts capable of sending shock waves racing through a barely understood seismic highway in its interior, isn't just a scientific curiosity. It's a genuine hazard consideration for anyone planning to spend extended time on the surface. Mission planners now studying potential landing sites for future crewed missions have to factor in not just the odds of a direct hit near a habitat, which remain extremely low, but also the possibility that a distant impact could send unexpected structural stress rippling through the ground beneath a settlement built on what looked, on paper, like stable terrain. This entire discovery also connects to one of the oldest, most stubborn mysteries about Mars, a puzzle scientists have been trying to crack for roughly 50 years. Since the 1970s, researchers have known that Mars is essentially split into two dramatically different halves. The northern lowlands stretch across about 2/3 of the planet's northern hemisphere, relatively smooth and low-lying. The southern highlands make up the rest, sitting nearly 3 miles higher in elevation, with a noticeably thicker crust than the north. This stark divide is known as the Martian dichotomy, and for decades, scientists have debated exactly what caused it. One camp argued that some unknown internal process reshaped the planet from within. The other camp argued that a truly massive collision, possibly with a moon-sized object or a series of smaller violent impacts, physically reshaped Mars's surface from the outside. Because the Martian surface is so ancient, pinpointing which explanation is correct has been extraordinarily difficult. But a new study published on December 27, 2024, used Marsquake data recorded by InSight to finally search for an answer buried deep inside the planet itself. InSight happened to be positioned almost exactly on the boundary between the northern lowlands and the southern highlands, which turned out to be an incredibly useful coincidence for this kind of research, since the lander had already recorded seismic waves traveling through the planet's mantle. The thick layer of rock sitting beneath the crust, researchers were able to compare how those waves behaved when they passed beneath the northern lowlands versus how they behaved passing beneath the southern highlands. What they found was striking. Seismic waves lost energy noticeably faster when traveling through the mantle beneath the southern highlands, which strongly suggests that region is significantly hotter underground than the mantle beneath the northern lowlands. That kind of temperature difference points toward an internal explanation rather than an external one, compelling evidence that whatever caused the Martian dichotomy originated from processes happening inside the planet, rather than from a single catastrophic impact from space. The leading theory now is that Mars once had shifting tectonic plates, similar in spirit to Earth's own plate tectonics, though almost certainly less dramatic in scale. As those ancient plates moved and the molten rock beneath them churned, they may have gradually carved out the difference between the two hemispheres. At some point, though, that tectonic movement simply stopped, leaving behind what scientists call a stagnant lid, a thick, motionless layer of crust sitting on top of a molten interior that used to be far more active. If that theory holds up, it would mean the mantle beneath the southern highlands may still be slowly pushing upward even today, while the mantle beneath the northern lowlands continues sinking deeper toward the planet's core, an ongoing, almost imperceptibly slow process that could help explain why the crust in the south remains thicker than the crust in the north. To be fair, scientists aren't ready to completely rule out the external impact theory either. Some recent research still leaves room for the idea that a massive ancient collision played some role in shaping the dichotomy, even if it wasn't the sole cause. Solving this fully will require even more Marsquake data and far more detailed models of how Mars originally formed, which is exactly why the seismic highway discovery matters so much right now. Every new confirmed data point, every impact-matched tremor, helps researchers refine these deep interior models a little further. It's worth noting that Earth went through something loosely comparable in its own deep past, when its own tectonic plates were first establishing the movement patterns that still shape our planet's surface today. The difference is that Earth's plates never fully locked into place, while Mars appears to have frozen mid-process billions of years ago, leaving behind a kind of geological fossil record that scientists can still read in the temperature differences buried in its mantle. What makes all of this especially remarkable is how much of it depends on data collected by a lander that has been offline since December 2022. InSight isn't sending back a single new signal. Everything researchers are learning now comes from painstakingly reanalyzing information the lander already recorded years ago. squeezing new insight out of old data using tools and techniques that simply didn't exist when the mission first launched. Artificial intelligence, in particular, has become the key that unlocked this discovery, transforming what would have been an impossibly slow manual search through tens of thousands of orbital images into a task that could be completed in a matter of days. That's not a small shift in how planetary science gets done. It suggests that huge amounts of valuable information may still be hiding inside archived data from InSight and other past missions, waiting for the right analytical tool to finally reveal what's actually there. Every Marsquake insight ever recorded is now a potential clue waiting to be re-examined, and researchers are only just beginning that process. Scientists have compared this moment to earlier eras in astronomy when old photographic plates, decades after they were first taken, suddenly yielded new discoveries once modern digital analysis techniques were applied to them. In much the same way, InSight's 4 years of listening may end up producing scientific breakthroughs for years, even decades, after the lander itself went permanently silent in the Martian dust. There's also a broader planetary safety angle worth sitting with. Mars doesn't have a magnetic field strong enough to deflect incoming space debris, and its thin atmosphere offers only minimal protection compared to Earth's. Combine that vulnerability with a genuinely higher than expected impact rate, and a newly discovered seismic highway capable of carrying shock waves deep into the planet's interior, and you start to realize just how differently Mars behaves compared to the relatively sheltered world we're used to living on. Every future robotic mission, and eventually every future crewed mission, will need to factor this evolving picture into its planning. Understanding exactly how often the planet gets hit, how far the resulting shockwaves travel, and what that says about the stability of the ground beneath any potential landing site isn't just academic curiosity anymore. It's becoming a genuinely practical safety question for the next era of Mars exploration. NASA and other space agencies are already discussing what an InSight successor mission might look like, potentially involving multiple smaller seismometers deployed at different locations across the planet simultaneously, rather than relying on a single lander sitting in one fixed spot. A distributed network like that would let scientists triangulate the exact source of a seismic signal far more precisely, distinguishing between an impact and an internal quake almost immediately instead of relying on years of after-the-fact detective work involving orbital photographs and machine learning. For now, scientists are left with a planet that has just revealed it's far more seismically active, far more frequently struck by debris from space, and far more structurally mysterious than anyone gave it credit for. The seismic highway running through its mantle raises immediate follow-up questions researchers haven't answered yet. How deep does this pathway actually extend? Does it connect to other regions of the planet beyond Cerberus Fossae? Could similar hidden channels exist elsewhere in the Martian interior, quietly carrying energy from impacts happening on completely different parts of the surface? And if the crust absorbs far less impact energy than previously assumed, what does that mean for the long-term stability of regions scientists once considered geologically quiet? None of these questions have solid answers yet, and getting those answers will likely require an entirely new generation of seismic instruments, possibly an updated lander mission, or a network of smaller, more distributed seismometers spread across different regions of the planet, since InSight alone was only ever positioned at a single fixed point. What began as a straightforward attempt to match old seismic recordings with newly spotted craters has turned into something considerably bigger, a fundamental correction to how scientists understand the inside of Mars. A planet once treated as geologically calm, its ancient volcanoes silent, its tectonic plates locked in place for billions of years, has just shown researchers that it's still capable of surprising them. Somewhere beneath that dusty red surface, a hidden network of pathways is quietly carrying the shockwaves of distant impacts across vast stretches of the planet, reshaping decades of assumptions along the way. And with new craters continuing to form more often than anyone expected, this newly discovered seismic highway isn't a one-time anomaly. It's an active, ongoing feature of a planet that is, quite literally, still being shaken by the universe around it, and scientists have only just begun to map where that hidden highway actually leads.